right, we're moving on to chapter 3, section 3.1. I'd like to give you a quiz, but there's nothing to quiz you on, right? There's no chapter 3 material that we've covered yet. So what I'll do is I'll include that information on a later quiz. How did you guys feel about the exam without talking about the questions too much? Did you feel like it was a fair exam? Yes. That's good. You better hope that that is how you feel. Because, you know, whether you think it's fair or not, it is what it is. Unless I was asking you to calculate the surface temperature of the sun, which is possible using statistical mechanics. That would be an unfair question because this is not a statistical mechanics course. So here's section 3.1. What's this about? Angle measure in radians. Ooh, finally we get to talk about that. Again, I have some grievances with this book right here. How the heck are you gonna talk about radians in chapter 3? That should have been like one of the first things to talk about. So, before we talk about radians, let's kind of talk about arc length. All right. We have our circle here. All right. I can, from here to here, traverse some angle theta, right? Theta. Our question is, what is this length right here? Let's see if I have a hair tie in here. I'll throw all these receipts. Who here has a hair tie that you don't mind me using? Can I break it? Yeah. Can I snap it? Yeah. Okay. Thank you. Everybody give a round of applause for Kinsey. She is sacrificing her hair tie for the sake of mathematics here. So, okay. We got a hair tie. It's a circle, right? So, our question is, if I go through some angle theta from here to here, how much is this length, this curved length? Notice we can't measure it with a ruler, right? I don't even have to snap this. I can give it back. Notice we can't measure it with a ruler because it's slanted. You can't measure something slanted with a ruler, right? It's impossible. You try and measure it, but then it curves. So your measurements will be inaccurate, right? But mathematics allows us to say, mathematically, if this is a curve, how much distance is it when I flatten it out and then measure it? That is what the arc length is. So actually, I can return this. I don't have to snap it. I usually like to break them. So that's the point. That's why this is even a thing. Because the ancient mathematicians wanted to know how can I measure something that's curved? It's impossible with a straight ruler, correct? You can't do it. But they developed mathematics to be able to solve that problem. So this little squiggly piece is called our S. And that's typically called your arc length. Okay? So it has been discovered that S is equal to R theta. In a circle, that is. The arc length of a circle, this only applies to circle. This does not apply to ellipses or any other shapes that have curves. This only applies to circles. S, the arc length, is equal to R theta. So for instance, let's say this circle represents the Large Hadron Collider in Geneva, Switzerland. Okay? It is a particle accelerator that accelerates protons to 99.99% the speed of light and smashes them together to create fundamental particles. And that is how the Higgs boson got discovered. What is a boson? Right? What's a boson? What's a proton? What's a lepton? What's an electron? That's really cool stuff. Okay, so let's say that the circumference of the LHC, I believe it's man, what was it, 10 kilometers? Maybe it's 5 kilometers, maybe it's 10 kilometers. Okay, so that's its circumference. Let's assume its radius is 3 kilometers. Okay, let's assume that this distance from here to here is 3 kilometers. Okay, so our R is equal to 3 kilometers. Our S, we don't know S. We know circumference, C, which is 2 pi R. Okay. And we say that this is equal to, well, I can actually calculate it. I don't have to guess what is 10. If the radius is 3, I can calculate the circumference is 2 pi times 3 kilometers. So it's 6 pi kilometers, which is approximately, what is 6 pi kilometers? That's actually more than what we were talking, 10. 6 times pi, that's like 18.84 kilometers. Okay, there's these huge structures that create very powerful magnetic fields and create environments on Earth that are very similar to environments a few seconds after the Big Bang occurred. But back to our trigonometry, I'm trying to tie it to something exciting here, even though trigonometry is exciting on its own. Okay, its circumference is this much, okay, 18.84 kilometers. Let's say the protons got accelerated through the accelerator, and the angle they make from their initial starting point here is, let's say, 77 degrees. What is this distance in kilometers, this S? From here to here. So if the protons have rotated through an angle of 77 degrees, how much distance have the protons traversed? You just use S equals R theta. Okay. This section, this mathematics allows us to get that curve and straighten it out and then measure it with a straight edge ruler. So S is equal to R theta. And then this needs to be my 3 kilometers. And we can't stick degrees in here. We cannot stick 77 in here. Because this equation is only true for radians. And now, it says radians, time for me to describe to you what a radian is. Well, just like kilometers measure distance and miles measure distance, they're two different units of measuring distance, right? One is a kilometer, one is a mile. They both measure distance, but they're different, right? A kilometer is shorter than a mile. And I don't know, what is it? 5 kilometers is like 3.2 miles. Okay? So a radian, I need to describe it off of a circle. Let's say we have a circle. It has a radius r. A radian, I tell you, is a measurement of angle. And so precisely 1 radian is when your arc length is equal, when you get the curve and straighten it out, it's equal to the radius in length. So let's say the radius of our circle is r. Our arc length is S equals R theta. Okay? But 1 radian is the angle you move to where when we straighten this out, it is exactly the radius of the circle. That is 1 radian. So 1 radian is equal to the angle you must rotate to generate an arc length of S is equal to your R. So that's a very important concept. So what is the relationship between radians and degrees? So this equation only works for radians, but we can convert from radians to degrees and from degrees to radians, just like how we can convert from miles to kilometers and from kilometers to miles and from miles to anything of another unit of measurement, feet. So can everybody see when I write down here? And back, okay. So how much is a rotation of a full circle in degrees? 360 degrees, very good. That's one in one revolution, in one rev, okay? So let's compare that to how many radians are there in one rotation? Well, theta is equal to S divided by R, right? Notice that when S is equal to R, you get theta is equal to 1. So you've only moved 1 radian. But to move the full circle, we say that you move 2 pi radians. Because the circumference of a circle of radius 1 is 2 pi. Okay. So this is equal to 2 pi in 1 revolution. Okay. It's just a different way of defining angle. Radians measures an angle. Degrees measures an angle. We just measure it differently. So until we convert this into radians, we can't solve the problem. Notice that this is a true statement, that for every 360 degrees, you have 2 pi radians. We typically denote that with rad, but we typically don't even talk about it at all. In our calculations, we don't keep writing 2 pi rad, 2 pi rad. We just drop that radian part because it's understood that anything is in terms of pi, and it's speaking about radians. So notice that, 360 is really like 2 times 180, right? So I can cancel the pi, the 2's out, and all that remains in the denominator is pi. So an equivalent formulation is that for every 180 degrees, you get pi radians. So when you move a half circle, you've moved pi radians. And when you move a full circle, you move 2 pi radians. Okay? So now this is our elegant derivation for, this is what we'll be using, this ratio. And notice this ratio, you can flip it upside down, okay? You can flip pi up top, 180 down, it doesn't matter. Why? Because this is equal to 1. And when I take the reciprocal of 1, it doesn't change anything. So that's why I can flip this ratio all I want. And we can flip it based off of what the problem that we're trying to solve gives us. So we are given that in the particle accelerator, in the LHC, the Large Hadron Collider in Geneva, Switzerland, our protons have been moved through 77 degrees. But we aspire to calculate how much distance do they traverse. So we have to convert this to radians. So I'm going to use this, but I want to end up with radians. So I'm going to put this 180 down here and this pi radians up here. Cancel out the degrees to get our answer in radians, because this equation only takes radians. Okay? So what does that give us? Let me use my calculator here. We got 77 and feel free to double check me with your calculator, times pi divided by 180. Oh, 1.34. 1.34. Approximately 1.34 radians. That's when I multiplied through the pi. I could have not multiplied through the pi and kept it in terms of pi. Both are equivalent. But when we want to find a standard measurement, we're going to actually multiply the pi through. So then this equation, I can replace the 77 degrees. I can place this 1.34 radians here, and we're going to be able to calculate the arc length. This is the distance that the protons have been accelerated through. So it's just my 1.34 times 3. Hey, come on now. 1.34 times 3. 4.02. 4.02 kilometers. Isn't that cool? We're able to calculate the distance they've moved through. And if you're a charged particle, and charged particles radiate. Who here, when they were a little kid, wondered what fire was? None of you guys wondered what fire was. You never wondered what is that thing, that flickery thing that's hot. You never saw fire when you were a little kid? Like a campfire? Did you ever like have a magnifying glass and use the sun to like focus it onto like a dry piece of leaf and have it catch on fire? You guys never played with fire growing up?
I did.
Yeah, but you never wonder what that stuff was?
No.
Yes, you did.
No, I didn't.
Yeah, you did.
No, I didn't.
Yes, you did.
No, I didn't.
Yes, you did.
No, I didn't.
You did, but you forgot. You did wonder.
You're crazy.
You forgot. But as a kid, we wonder what is everything, right? Maybe you can't remember it, but if you've ever interacted with a kid, you realize that they ask questions about everything. What is light? What is fire? What are rocks made out of? What is water made out of? You know what I mean? I choose to not believe you. I'm not calling you a liar. I just think you probably forgot. You must have remembered. You must have thought, what is this stuff? Fire is actually a plasma. Who knows what a plasma is? What is it, too early in the morning for you guys? Plasma is the fourth state of matter. We got solid, we got liquid, we have gas, then we have plasma. Who's seen lightning strikes? Yeah, that's plasma. Fire, that's plasma. What is plasma? It's when a gas, its atoms lose hold of its electrons, and the electrons just get to move freely through the gas. And an electron is a charged particle. And so as it moves freely through the gas, it radiates light. This is a fundamental thing we found about nature, is that charged particles, whenever you accelerate them, they radiate light. That's precisely why fire is hot, because it's radiating a lot of light. You wondered what fire was. I don't believe you. All of you wondered what it was.
I never knew what plasma was.
You didn't know what it was, but I'm sure you were wondering, what is that? Like, how is that even happening? Here, let me ask Joshua. Joshua at home, did you ever wonder what fire was? Let me check the chat over here. I still haven't fully explained what fire is, but it is a plasma. That's the short answer. Now that we've described a radian, we've calculated an arc length. Let's do one more example. Let's say I have a circle. Let's say it's a circle of radius 3, and I've traveled a theta, and my theta is equal to pi over 3. How much arc length have I moved through? No, I just thought it was cool. See, I don't believe you guys. I don't believe you guys, man. Okay. So I didn't give any units. I just said it's a radius 3. I didn't say 3 kilometers. I didn't say 3 miles. I didn't say 3 inches. I didn't say 3 feet. I didn't say 3 millimeters. It's just 3. So if there's no units, you can still do the calculation. It would just be a unitless calculation. So we aspire to find this arc length S. S is equal to arc theta. So S is going to be equal to our radius 3 times our radians that we've rotated through, pi over 3. And so the 3's cancel. So we get pi is equal to our S. So you know, pi, 3.1415 with infinitely many unpredictable repeating integers after that. Okay, so here's another situation. What if I give you an arc length? Let's say S is equal to 4. Okay. And what if I give you the radius of your circle is 13? What is the angle in which you rotated through? So it's a circle of radius 13. And you've moved through some angle. It's unknown what that angle is, but it is known what the arc length is that you rotated through. The S is known, and that's equal to 4. What is that angle that you rotated through? And how can we discover this mathematical quantity? Because it applies to a circle, we can utilize the equation S is equal to R theta. We aspire to find what theta is equivalent to, so we can algebraically solve for it. Right? Divide both sides by R to solve for the variable theta. Because S is known, that's a 4. R is known, it's a 13. So that's what theta is. It's 4 over 13 radians. Let's say you are given a circle. You are given that it rotates through pi over 4 radians. And you are given that that creates an arc length of 22. What is the radius of this circle? You're not given this radius. You just know that we rotated pi over 4 radians, and that the arc length that that generated was 22. It could be kilometers, it could be feet, whatever. We can scale our circle to whatever scale we want. What is the radius? It's a circle, so S is equal to R theta applies. Well, I just solve for R. S over theta is equal to my R. So that means I get 22 divided by pi over 4. And I multiply by reciprocals, because that's 22 over 1 times 4 over pi. And that equals, I don't know, 88 over pi. That's my R. So whatever this works out to be, let's do it just for curiosity's sake. 88 over pi. Well, it works out to be around 28. So this circle has a radius of 28, approximately. Isn't that amazing? Let's say you're on, let's say you're around like a patch of a forest that's almost approximated to be a circle, and you measure some amount of like walking distance around the forest, right? And then you say, okay, how much angle did I move through? Okay, well, I can calculate the radius of the forest, and then I can calculate the diameter of the forest without even having to go through the forest. Maybe the forest is so dense that you would need a lot of people and a lot of machetes to cut through it, and you don't want to do that because you want to damage the biodiversity. You can calculate the distance across that region if it approximates to a circle. Notice that you can then do this across the whole forest to calculate how much a forest is, because you can sum all the diameters up. The possibilities are endless with mathematics. Okay? So, now, let's connect radians to degrees even further. Namely, let's show what our favorite angles are, our special angles, at the radian value. Recall we have this unit circle. Recall you had a situation like this, where this is 0 degrees, this is 30 degrees, this is 45 degrees, this is 60 degrees, this is 90 degrees. What is it in radians? Well, 0 degrees is 0 radians. So, rad. But what is 30 degrees in radians? Use our wonderful conversion here, that in 1 radian, you rotate 180 degrees, cancel out the degrees, you get 30 divided by 180 times pi. What does that give us? Pi over 6. Because 30 divided by 180 is the same thing as 6. 1 over 6. It's the same thing as 1 over 6. So when you multiply that times your pi, you get pi over 6. Let me be more explicit in what I'm talking about, even though you might probably already understand. This is equal to 3 times 10 times pi. And this is equal to 18 times 10 degrees, but the degrees canceled. So we cancel out the 10s. So I get 3 pi all over 18. But 18 is also what? 3 times what? Cancel out those. I get pi over 6. Oh, so 30 degrees is the same thing as pi over 6. What about 45 degrees? Well, again, you can utilize our formula here, that in 1 pi radian, you rotate 180 degrees. This equals pi over 4. How do we get that? I mean, take a look. 45 is really 9 times 5, right? Times pi. What is 180? Again, it's 18 times 10, but that's really 18 times 2 times 5, because 10 is 2 times 5. We can cancel out these 5s here, leaving me with 18 times 2, Well, 18 is really 2 times 9, right? Notice I can cancel out these 9s, and then I get that that's equal to pi divided by 2 times 2. Now I talked about the fundamental theorem of arithmetic in here, that every composite number can be decomposed to a product of prime numbers. That's what I'm doing. I'm just decomposing this composite number into a product of prime numbers. What is 60 degrees? Well, use this conversion again, and we get that 60 degrees is pi over 3. What is 90 degrees? Use our conversion. Get pi over 2. Okay? Well, what if I'm given a radians and I want a degrees? What about 2 pi over 3? How many degrees is that? We utilize our conversion, but we just go the other way. Well, 2 pi over 3 is a 2 pi over 3 radians. We drop the radian usually when we talk about it, but it's always there. It never goes away. It's just implied. So we utilize this equation right here, this ratio, and we utilize the fact that that ratio is equivalent to 1, so we can flip it all we want. And I'm going to flip it because I want to put that pi radians downstairs and that 180 degrees upstairs, because I aspire to get my final answer in degrees. So this equals 120 degrees, because also don't forget these pi's can cancel. So I'm multiplying 2 divided by 3 times 180. How does that equal 120? Well, 2 times 180 is the same thing as 2 times 18 times 10 degrees, all divided by your 3. But notice that this is 2 times 3 times 6 times 10 all over 3. Right? 6, 12, 18. Yep. Cancel out some 3's. Then I get 6 times 10, which is 60. And when you double that, it's 120 degrees. I love it. A few of you, if not all of you, have this look on your face like, wait, I can't believe that you're like explaining it in a way in which is so clear and it's understandable. And I've never had that before. Feel free to rejoice. Feel free to rejoice up in here. So actually, this is going to be 120 degrees, and that's equal to 2 pi over 3. Recall the unit circle. It still has that pattern where you go 30, 15, 15, 30. So although we've calculated what 30 is in radians, that's pi over 6. We have yet to calculate what 15 degrees is, so we'll just do that. And then, as an exercise to you, I will let you complete your unit circle all in radians. Because you know, then the next angle here is 135. And the next angle here, 15, 15, so that's 4 becomes 150 degrees. Is it 150? Because when I add 30 to that is 180. Yeah. 5, 6, 7, 8. Yep. Okay. So let's see what 15 degrees is here, because then we can complete this chain. Because I know what 30 degrees is. This is pi over 6. What is 15 degrees? let's use our conversion here, cancel out the degrees. Our final answer is going to be in pi radians. So this is pi times 3 times 5, because that's what 15 decomposes to. And down here, I get like 18 times 10, which is the same thing as 18 times 2 times 5. Cancel out some 5s. Is there anything else we can cancel? All we can realize that 18 is really 3 times 6, is it not? 6, 12, 18. Boom. So I can now cancel some 3s. Something went wrong here. Oh, it's because I forgot this 2. I forgot to bring this 2 over here. Right? I dropped the 2. 2's get dropped more than any number. We're always searching for factors of 2. Poor 2. 1 is the loneliest number, but 2 is the most ignored. So 15 degrees is pi over 12. So if you aspire to derive what all of the special angles on the unit circle is, or what they are, all you have to do is apply this 30, 15, 15, 30 rule to the radians. So notice that from over here at pi over 2, I was able to attain 2 pi over 3 by adding 8 pi over 6, because the 30, 15, 15, 30 pattern repeats. And so pi over 2 plus my 30 degree analog in radians should give me that 2 pi over 3. Let's check. Multiply top and bottom by fancy number 1 to establish a common denominator. So I get 3 pi plus a pi all over 6. This is 4 pi all over 6. This is 2 times pi over 2 times 3. Cancel, cancel. That's 2 pi all over 3. So do this process and you can derive all the special angles. I won't do it in class. What? Well, maybe I will do it in class. This chapter is all basically done. What? This is such a short chapter. Maybe I should move on to the next chapter. Let's see here. I might move on to the next chapter. And here's why I might do that. I have not graded your exams yet, and not everybody has done with it. So because of that fact, I want to spend some time reviewing the exam once everyone's taken it. So because of that fact, to generate some more time to insert that in there, what I'll do is I'm moving on to 3.2. But I won't make your 3.1 and 3.2 due on the same day, okay? So your 3.1 will be due on Tuesday, your homework for 3.1. And your 3.2 will be due on Thursday, even though we've covered it, okay? That way I can slot in some time for a review of the exam and how to do the problems. Even though that shouldn't take too long. I always like to do that for my students. When they take an exam, I like to go through the problems once they're done to show them how you do it. Because guess what, guys? Mathematics builds upon itself. And you may slip up at the beginning, but if you learn how to do it, then you can pick yourself up for the rest of the semester. And mathematics is comprehensive in nature. It just is comprehensive in nature. And furthermore, our final exam will be comprehensive in nature. So it will help you on the final exam as well. Furthermore, I will upload it on the Files tab in Canvas so that you can access that information later on. I just want all of you to succeed. I want to prepare you as much as I can for you to be successful. But after that, the ball is in your court, if you will. Let's go to 3.2. So arc length, velocity, and area of a circular sector. All right, so we kind of already talked about arc length. Wait a second, did they not even bring up S equals R theta in this previous chapter? Yes, they did. They subtly did. Okay, so now they're explicitly saying S equals R theta, even though in 3.1 they said theta is equal to S over R. Okay. So let's talk about angular and linear velocity. Angular vs linear velocity. Sounds kind of cool, huh? So who can give me an example of linear velocity?
Y equals X.
Y equals X.
Would that be considered linear because it's a straight line?
Yeah, well, that's correct. We call Y equals X like a line. So I can see what you're saying there. You're very close and you're expressing it mathematically. So that makes me very happy and very proud. But it's not just linear, it's linear velocity. What is that velocity thing about?
It's velocity, mass times acceleration.
Mass times acceleration. That's force. Mass times acceleration is force. We talk about Newton's first law. M, force is equal to ma. So that's force. This is linear velocity, right? I'm sprinting. You guys are talking about suicides this beginning of the class. You're like, oh man, them suicides. What do you guys running suicides for?
To get condition.
For what?
For football.
Oh, you guys football players?
Distance over time.
You what?
Distance over time.
Oh, distance over time. Yeah, for sure. Because what happens when they say your car is going 60 miles per hour? Miles is a distance, per is meaning divide, and hour is a time. Okay. So now we got what velocity is. What is like linear velocity versus angular velocity? So I keep doing this because what am I traveling in?
Straight line.
Straight line. So this is linear velocity. Whereas if I'm like, or 360 roundhouse kick, the speed is moving through a circle or some type of angle. When something is fixed about a radius and it's rotating, that velocity becomes angular velocity. But when something is just moving in a straight line, that velocity becomes linear velocity. I think about it like this. It'll hurt really hard if someone runs into you and tackles you right away. And it'll hurt really hard if someone's spinning and then you knock into them. They both have velocity. Oh, so like it's like a straight punch versus a hook. You know what I'm saying? Like they both hurt. One is linear in nature, the other one is rotating in nature. Both gonna hurt. Okay. Another thing you can think about is a car. Wheels on a car. The interesting thing is cars drive, and they have linear velocity, right? They're just moving in a straight line. But what are the tires doing?
Rolling.
The tires are rolling for you to be able to move, right? So actually the tires have angular velocity. Their angular velocity is generating the linear velocity of the car. You guys getting the difference here? So velocity is distance over time. So linear velocity is linear distance over time. Whereas angular velocity is angular. Angular. Is it lar or lur? Angular. I have no I have no idea whether it's E or A. You guys gotta forgive me. I'm not the best speller. I never was in the spelling bees. Angular. Who knows if it's an A or E? It's an A. Thanks, man. Angular distance over time. Okay. What is the angular distance? Hint, hint. It correlates to what we were talking about earlier in section 3.1.
Arc length.
Yes. Woo! Yeah. Arc length. How much arc length is it going through per unit of time? That's how, huh?
It's 360 degrees.
Yeah, you're barking up the right tree. It's so when something is rotating, it's going through an arc length. And yeah, if it rotates in one full revolution, it's 360 degrees. And that's 2 pi radians, and we can calculate what the arc length is. In that case, the arc length is the circumference of the circle, right? Because if you move throughout the whole circle, the arc length is the circumference of the circle. You see what I'm saying? S is equal to r theta. But if r is equal to 2 pi, or I mean, if theta is equal to 2 pi, you get this, 2 pi r. When arc length is equal to 2 pi r, this is the same thing as circumference, is it not? The circumference of a circle is 2 pi r. Look, we derived the circumference of the circle formula just by applying the arc length formula to a full rotation. This is why they tell you the circumference is equal to 2 pi r. Isn't that cool? Isn't math cool? Yeah, it's very cool. Okay, so let's talk about angular velocity. It's something we call omega. And omega is equal to a theta over time. Whereas linear velocity v is equal to an r theta over time. Clear up some board space here. So you can think about it as omega, which is our angular velocity, as how much angle theta are we rotating per time. If I'm rotating through very little theta per time, my angular velocity is really slow. But if you rev up that value, angular velocity gets higher. Ooh, everything's spinning. Over here, notice that this r theta is equal to s. So it's a distance over time. And s is an arc length, but we linearized it. It's no longer curved. The equation allows us to get that curve and straighten it out and measure it. So that's why that's there, even though it seems like it shouldn't be. So without further ado, let's say we got a car, and let's say it's a truck. I should make the wheels bigger because I need to talk about these wheels. Let's say the radius of the wheels is 3. If the car is moving at 60 miles per hour, and the radius, what are rims usually? This is because it's kind of like a monster truck. So what would the rims on a monster truck be? We'll look this up here. What is the diameter of the tires of a monster truck? So it says 66 inches high, 43 inches wide. So we know that the diameter is 33 inches. The diameter is 66 inches because it's saying monster truck wheels are 66 inches high. So that means its radius is what? 33 inches. Who here likes monster trucks? He was like, oh yeah, actually I do like them. Is that a phone? That should not be a phone. So, what is the angular velocity of the wheel if the linear velocity v is equal to 60 miles per hour? What is this omega here? And yes. So this is a really cool problem here. Actually, omega, I've drawn it like a line, but really this omega is like a curve, right? Omega is like rotating around the wheel. So what we want to discover is how fast is the wheel rotating? How would we do this, guys? Because what we want to know is what is omega? And that is theta over t. So we got to figure out how many radians is it rotating through per unit of time. So first, we have to convert this 60 miles in 1 hour to something, right? That's the only piece of information we have. I want to know how much is it rotating? How fast is it rotating? What theta over time is it going through? And actually, let's say I want omega in radians per second. I want to find this omega in radians per second. How will we do this? Any suggestions? We probably should start working up here. The only piece of information that we've been given is that this thing is moving at 60 miles in 1 hour. We aspire to find our final answer in radians per second. Okay, so right now, what do we have? We have a distance per time. What I want is an angle per time. So somehow we have to convert that distance into an angle, and somehow we have to convert that hour to seconds. I know how to do that hour to seconds part. That's really easy. Let's just bloody the sword real quick and do that one first. I know in 1 hour, there's 60 minutes, right? So I can cancel the hours. And then I know in 1 minute, there's 60 seconds. I can cancel these guys out. So what do I get? I get miles per second once I'm done with this. 60 divided by 60 divided by 3,600. right? Because 6 times 6 is 36, but 60 times 60 is 3,600, right? 36 with 2 zeros on it. So this ends up equaling 0.16 miles per second. Wait, is that? No, it's 0.016. I thought that was a little too fast. Miles per second. Every second you're moving 0.16 miles. It's kind of cool. Because we achieve this kind of speed when we're on the highway. Okay. Now, I have it in a length over seconds, but I need it to be a radians over second. What am I going to do, guys? How can I achieve this result? So I'm going to bring this down here to continue our calculation. I'm going to have 0.016 miles per second. I didn't change anything. I'm just rewriting it. But I'm going to need to multiply it times something. I definitely don't want to change that second. I want that to be there because our final answer should be in radians per second. What I want to alter is that miles. How can I connect a length to an angle? Oh, hint. The tires are circles. Oh, hint. The only way a car can move forward is if the tires do what?
Rotate.
Yes. So what is happening is moving through what? Some type of what? When it rotates. It has to go through some what? Yes. Yes. Its rotation generates an arc length. So when the wheels move fully once, how much distance did the car travel? In one revolution of a wheel spinning, or in this case, a monster truck's tires, in one revolution, how much distance did the monster truck move forward?
0.060.
So that's how much distance it goes per second.
Yeah.
That's not how much distance it goes per rotation of the wheel. Does that make sense? How it's not necessarily the same? That is how much distance is it going per second? I'm asking how much distance will it go per one rotation of the wheel? This is where I might want to get that hair tie and actually break it. Imagine if I broke this. I'm not trying to break the hair tie. I'm not trying to get chalk on it either. I can break it?
Yeah.
Yes. So, look guys, imagine this is the wheel. I want to know what linear distance did the wheel move in one full rotation. That's equivalent to getting the wheel, flattening it out. How much is this distance? It's the same as the circumference of the circle. Right? When you get this circle, you say, what's the circumference? You generate a value, and that's this value when you measure it straight. Is it not? Just nod your heads if you agree with that part and that part only. You all agree. Very good. Boom. You have sacrificed this for the greater good of mathematics. Ooh, cool. So in one revolution, how much distance does this move forward? And in order to answer that question, I need to convert from miles to inches because our equation for circumference of this circle will be in inches. So I don't want to have miles with inches. I want to convert miles to inches. And what is that? How many? So 12 inches in a foot, right? I got, is this right? 12 inches in 1 foot? Okay. So how many feet are in a mile? Does anybody know? 5,280. Yes! We found a connection between inches and miles because we can connect miles to feet and feet to inches. This is very important in mathematics to be able to convert through units. So in 1 mile, I have 5,280 feet. And in 1 foot, I have 12 inches. Cancel, 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 cancel. So then this becomes inches per second. And I see people calculating away, and it just warms my teaching heart. It makes me so happy that you guys are like involved in trying to do this stuff. I'm very proud of you. I'm going to try not to cry right now. Tears of happiness. Oh, wait. Put a times here. There we go. 0 point. So I'm multiplying the numerators because in the denominator there's nothing but ones. So I'm 0.16 times 5,280 times 12 is going to be 1013. There's some decimals, but we'll forget about that. Actually, we'll just round it up to a 4. Is that what you get? 1013.76. Yeah, I'm just going to round it up to a 4. This many inches per second. This is very good because now, remember, we can convert in 1 revolution. How much distance does it cover? Why do we care about doing that? Because once we do that, we can talk about the angle. When we talk about circumference in a circle, we can connect it to angle. Okay? So then, now that we're here, if it's moving this many inches per second, how many inches, question mark, inches in 1 revolution? How many inches will it rotate per revolution? It's the circumference of a circle. The tire rotates once and it moves through a circumference in length. It moves through a circumference in value. So the amount of inches is 2 pi r. Our r is 33 inches. Does that make sense? Pay very close attention to this problem because who knows? You may see this kind of a problem on your next exam. It's a good thing that you have this video to rewatch it and you have your notes. But please pay very close attention to how I'm logically going from the next step to the next step to the next step. That's the most important thing, is the step-by-step reasoning. We're step-by-step inching towards the answer. Seems like it's far off, but if you just keep doing this one foot after the other, you're going to get closer and closer to the final answer. So I'm going to delete these formulas because they're in the way right now. So what does this equal? 1. So this answer divided by 2 pi times 33. Answer divided by 2 pi times 33. 4.89 approximately. 4.89 revolutions per second. If this monster truck is driving 60 miles per hour, it goes through 4.89 revolutions every second. The tire rotates almost 5 times every second. And that's a big old tire too. So you know it's like, but guys, I aspire my final answer to be in radians per second, a theta over s, or a theta over time, which is s in seconds. I have revolutions per second. But how can we correlate rotation and a revolution to an angle? We aspire to calculate the angular velocity of this tire by just purely the given information of how fast is a car moving in a linear fashion. So I want radians up here. In one revolution, I want to get rid of that revolution. In one revolution, I sound like a dictator. I want to get rid of the revolution. Must crush the revolution. How can we correlate this to a revolution? Because if I can say in one revolution, there's something, and it would produce radians on top, then we're done.
Is it 2 pi? It is 2 pi because it's 360 degrees.
In one revolution, there's 2 pi radians, right? Boom! Booyah shaka! So it's 4.89 times 2 pi, and we're done. This is the reasoning. I want you guys to think like this, because then you'll be able to reason your way through the whole problem. So this ends up becoming 30.72, approximately. Radians per 1 second. We're done because we converted the known piece of information through a step-by-step process of logical reasoning to angular velocity. So what does this mean? Actually, it would be more interesting to keep it in terms of pi. So let's get that 4 point. Let's get that 4 point. I should delete this pi here. This is the same thing. When I don't multiply, this is when I multiply through the pi, okay? But it doesn't make as much intuitive sense as leaving the pi there. So This is actually, if you don't multiply through the pi, 9.78 approximately. 9.78 pi radians per 1 second. Let's think about what that means here. That's almost 10 pi radians per second. That means the wheel rotates how many times almost per second? Assume that value is like 10 pi. It's almost 10 pi, right? So how many times does it rotate per second if it's rotating 10 pi radians in 1 second? You guys accurately asserted that 2 pi radians is in 1 revolution. So how many revolutions is there in 10 pi radians? Okay. 1 revolution, 2 pi, 2 revolution, 4 pi, 3 revolution. Yes. 5. It's approximately 5 rotations per second. And look, we already had that here. It was approximately 5 rotations per second. That's why this makes sense. The result makes sense. So, and what?
That makes sense.
It does make sense, right?
Yes.
Yes, it's important to analyze your final results whenever you do calculations. Not only in math, but in everything in life. You need to rethink your analysis of the situation. So this answer makes sense. You could have left it like this, or you could have left it like this. Potato, potato, tomato, tomato, it don't matter. It is 9:14. You guys have been excellent today. I'm gonna give you that extra minute of your life to go do what you want. You guys have been very good today. What position you guys play? You what? You're a linebacker? What about you?
I play defensive tackle.
Wow. That's really cool. I played linebacker.
You play football?
Yeah.
Are you serious? You got 3 majors?
Well, I didn't play football in college. I played 1 year of football. I played 1 year of freshman football in high school. And my mama made me quit.
Really?
Yeah.
Why?
I was too good at it.
Just tell us why. Why'd you quit?
I was too good at it. She made me quit.
How did you? Okay.
She was scared I was going to go pro, and that's not what she wanted.
It's freshman football.
I know. But
That's a long way away.
go talk to my mom, man. Go talk to her about it. I didn't do it.
It's not logical.
My teammates and my coach were really sad, but I played strong linebacker.
Strong side?
Yeah. It was really fun. I love firing. Is that what you guys call it, firing? Whenever you blitz? Blitz is when all the linebackers fire, right? Yeah, I love to fire. That is my favorite thing. Sacking the quarterback. It feels good.
What division were y'all in?
I played at Putnam City Original. Down the street from here.
Around here then.
Yeah, I'm from here.
Snap, dude.
Yeah.
That's awesome.
Yeah. Thank you very much. I need to speak with you.
Okay.
I got your email.
Okay.
When can we do this? When are you available?
I mean, I'll be here all day tomorrow.